Hello and welcome to Algebra 2 with Mr. Clausen. Today we're going to talk about the reciprocal function family. And in this video we're going to talk about the basic format of reciprocal functions, look at some basic graphing and what their format looks like, as well as how to create functions based on the asymptotes of inverse functions or reciprocal functions, and then finish off with a simple real-world example. So let's get started. And to give you an idea of what a reciprocal function looks like, it generally has, well, it's an inverse function. If you have a basic inverse function like this, you have this basic restriction where x cannot equal 0 because you would get a infinite number, you get a 0 in a denominator. And so when you have x equals 0, you tend to get this unique behavior that observes that you can't cross this imaginary boundary, and we refer to these boundaries as asymptotes. All right, and we've talked about these a little bit in the past, but we're going to be making a little bit of a visit with them again. And what the basic format for a parent function, this would be your generic parent function for the reciprocal function family, simply just gets infinitely closer to the x-axis as you go to negative infinity, and then it starts to break away a little bit and then forms a mirror image here and starts to do the same thing down here, that as you approach the y-axis it infinitely gets closer and closer and closer and closer, never touches it but gets closer and closer and closer. And then since it can't touch x equals 0, it will jump up here and the sign will switch as soon as x becomes positive. And so you'll get a function that looks like this. And if you ever see on your calculator like this huge like sharp spike up and then back down again, that spike up that you may see on a graphing calculator actually does not exist. It's just a way for the calculator to try to estimate and determine like where this function's supposed to be, because it's making all these guess values about where these points are and how the line should be drawn. But a reciprocal function is just going to be these two separate branches that represent the overall nature of the function. Now you have this function, and if you put a minus sign on it, you could imagine, much like, parabolas and some of these other functions, is you just get this mirroring across the x-axis. So just like this function, it's the exact same thing, except that it will just mirror image here, and it'll do something like this. And try to draw this to the best of my ability here. And then you'll go down here a little bit, touch, and then switch over. And I'm trying to make this as symmetrical as I can with what I have here, but you get this general behavior from a inverse function or a reciprocal function in this given case. Now, I show this function over here because this is the combined format for the reciprocal function, where you have h that represents the horizontal shift, and the k, which represents a vertical shift. So just like it did with parabolas or with other types of functions that we've talked about previously, you have this same behavior that occurs. So when you have 0.4 for your a term, well, that really shrinks everything. And so instead of maybe your functions looking like this, you would get a behavior that looks a little more like this, where when x equals 1, y would equal 0.4, for example. So you're going to get something that's very like that. And I would say those are some of the most important points, is like when x is equal to 1, and then you're going to have that mirror image. And so you'll see that it hugs the origin a lot closer. And we'll see here that I tried to intentionally hit this point right here in both of these graphs. When x equaled 1, y will equal 1. That's probably one of the most important points that I'm looking at when I'm just trying to trace this, because you're going to get this mirror imaging. It takes a little bit of, skill to kind of go and draw that out, but then now y equals negative 0 or 0.4 when x equals negative 1, and then it'll just kind of rotate there, and then it'll go down. And so you'll see this really tight hugging occur when you shrink it, and then when you expand it, you would get the exact same thing. So so when x is equal to 1, 1, 2, 3, 4, 5, 6, y would equal to 6. And x equals negative 1, y would have to equal negative 6. And so you will get, behavior that'll look like this. I'm just drawing out a couple points. Based on that, you can make a table to do this. There's a few different ways that you can go about it. But the overall idea that you should be getting at here is that this function is going to curve out much more and be stretched out as a response to that increasing of the a term, right? And so it's just some general behavior things to keep in mind when you're looking at the basic format of these reciprocal functions. Now, if we want to graph by identifying asymptotes and those type of things, though, that is definitely something that you want to take into consideration. So for example, this is your general parent function, right, that you are used to, or at least saw an example of previously. And the other thing that you want to take into consideration here is that if you want to graph it, this is a vertical shift. And so this basic behavior that I just got done showing you can be duplicated, and you will have a vertical shift at x equals 0, because there is no h term, and then the horizontal asymptote will be at y equals negative 3, since k is equal to negative 3. And then, like the general behavior, when at 1, when x equals negative 1, y equals 1, well, that same type of behavior will exist. It'll just be down there. And so, we can just go draw this out, relative tightness there, and then again, not my best drawing, but the main idea that I'm trying to illustrate here is that if you want to graph these functions, the main thing that you want to take into consideration is if there is a k or an h value, we can look at those, we can draw the asymptotes out, and then we can get a pretty good sketch of what a inverse function will look like as you apply these different horizontal or vertical shifts. This is another great example. So here we have h is equal to 4, so that is a rightward shift of 4. And so based on that, there will be a vertical asymptote here. And then the horizontal asymptote will be here. Since there is no k value, k is equal to 0. And so the same type of thing will occur since that's a 1, all right? In that you will have a point there and a point there. And again, just drawing this to the best of my ability. It never touches the asymptote, but it will ever get closer to it. All right, and so again, just drawing these general shapes. Here we have an example of a horizontal shift. Actually, h is equal to 2, k is equal to 5. So 1, 2, 3, 4, 5. So we have this vertical shift. We have this horizontal shift. And so now, it never touches that line, but we'll ever get closer to it. Same there. All right, we'll just, yeah, see, it never touches. All right, and so again, just giving you some really basic idea as far as the general behavior. H is equal to 4, so just like the example above, you'll have the same type of behavior occur. But when, let's say x equals 5, y is equal to 6. And again, you'll get the same behavior. It'll just stretch itself out. And you'll get a function that looks like this. And so you get some general behavior here that is relatively easy to graph once you get the basic emphasis of how the horizontal and vertical translations occur. So how can we create some functions based on these asymptotes? Well, it's relatively easy once you get the basic premise of what's going on here. So for example, this is what a typical reciprocal family function looks like, and or an inverse variation, I should say. And if you go, you can pretty easily see, especially if you get the zoom just right, that there is a horizontal translation at y equals 4. This indicates as a vertical shift of positive 4 for k. And if we go and we look at the vertical asymptotes, the vertical asymptote is here because of the horizontal shift of h equals 2. And so if you can identify these lines that are formed by the horizontal and vertical shifts, well, it makes it pretty simple to just go. And for any of these examples that I show, unless it's indicated differently, you can assume that these are just shifts from the basic parent function, which I have here. If I wanted you to find a different value for a, I would have to give you like 2 points along one of these lines so that you can plug them in and then find those values. So we're going to assume that, this is a value of 1 here, and then we just go x minus 2 since h is equal to 2, and then plus 4. And this is how you would make a model for this given function. Now, the last example that I want to talk about is a simple real-world example that we're going to look at here. And this is a situation where a local restaurant spends $1,200 a year on employee prizes to promote the selling of gift cards. And this is a pretty common thing, to boost morale, to get people motivated. Like, even if you think about the school and when we were trying to encourage people to advertise the Christmas challenge or invite new families to the school, we were doing prizes. So like if you sent out a certain number of emails, you could get a prize of a certain amount, and if you actually got families to sign up based on your recommendation or referral, you got a bigger prize. And so we're going to look at this type of situation, but based on a reciprocal function. So let's say our local restaurant spends $1,200 each year on employee prizes to promote the selling of gift cards. The amount spent on each prize is dictated by the number of prizes given out. Makes sense. Create a function that models the relationship between the number of awards given and the value C of each award. Determine a reasonable domain and range for the function. All right, so since we're talking about inverse variations, I'm going to go out on a hunch here and say that it's probably going to fit this type of model. And now what we need to do is we need to figure out what we're going to assign what. All right, so I would say that if you have a constant here, that your constant is probably the amount of money that you're spending on prizes. All right, so this is going to be your constant of variation for this given instance. Now, the amount spent on each prize is dictated by the number of prizes given out. That would probably be x, because x is being divided by the total amount that the restaurant has to spend, right? And the number of awards, they want you to label as A, which is the number of awards, and y is going to represent the z that they want you to dictate, and this is going to be represented by the value of each award. Now, it might be fair to say to create an inverse function, for this given situation, based on the previous video that we just had on here. But in this given situation, what I want to show you is that there are some of these relatively simple circumstances that we can apply these functions to and go and find some pretty useful information. And so based on this, we can just plug these in, and the function that would model this relationship would simply be C is equal to 1200 all over A. Where, if you have 10 awards, the value of each award, or the cost of each reward, is going to be 120 bucks. If you have 100 awards, the cost of each reward is going to be $12. And so it lends itself really nicely to this specific modeling. Like if you want to know and just kind of compute this out or have a graph of it, it's going to look like these reciprocal family graphs that we've been drawing. Now, one of the things that I want to do here in this given example, though, is talk about a reasonable domain and range, all right? And there's a reason for this. So first of all, if you go and you graph this relationship, keep in mind that, you will have the positive variation like this, where this is x and this, or sorry, this is x and this is y, but you'll also have the negative variation, all right? And what I'm going to point out here is that this is not a possible representation of the situation that we're looking at. And so what's important when we're looking at some of this is that we set, realistic domain values given on this situation. So the domain, the range of A values here, okay, so this is A and this is C, is going to be, technically 0, because you can't have more than 0 prizes. It actually has to be larger than 0, so let's actually write that even differently. Let's say 0 greater than 0, and we could technically say infinity, but maybe we should say a prize has to be at least a penny. So, let's say 120,000. So A has to be greater than 0, but less than 120,000. And I think we're at that level of mathematics where we can go and say, hey, all right, what's like realistic here, all right? 120,000, you got to have a prize more than a penny. Maybe, you want to even go further than that. Maybe if it's a gift card has to be at least $5, so in that case, if it's at least $5, 100 gift cards would be $500, 200 would be 1,000, 240 would be the $1,200. So you could go that route as well. I think this is definitely kind of the maximum territory that we're looking at in terms of gift cards. I mean, could you imagine getting a 1 penny gift card? It'd be like, oh, thanks, whoopity-doo-dah-day. I mean, the plastic costs more than that. But I digress. So that's a situation where we're looking at domain. Now, range is the same type of situation that we need to take into consideration here. So based on the values that I have here, our range has to be 0.01 at a minimum, right? It has to be equal to or bigger than that, and can have a maximum of $1,200 because that's the total amount of money that we have on prizes. It's the range of Y values that's indicated here. And this is, like I said, important again, because if we accidentally find ourselves in this other part of the function, it's important to establish that that's a realistic constraint that we have to deal with. So just a few things to think about. But with that said, I hope that this video gave you a nice introduction into reciprocal function families, looking at inverse functions and the graphs of them at a little bit deeper level, how to trace asymptotes based on that combined equation, and looking at a simple real-world example. And with that said, let's do some math.